Testing, testing. Well, that's not very high. Move that. Oh, that's all the way. Testing. Yeah, the volume's kind of low. Testing. That's too bad. Testing, testing. That's a little weird. Testing. Okay. Okay. As I'm getting started. Now, I gave you this last day, right? Yeah. Okay, Jonathan. Right. What I would like you to do, get this down. We are going to do the Bohr model of these. So if you could draw the Bohr model of the first three very quickly. Review of a couple of terms. And then people who didn't get the sheet from last day, put up your hands. And then we'll come around. Just the two. There you go. There you go. Laptops away. As we're getting started. Google Classroom. Alexander, Anton, Cahalan, Donald, Evan. Evan's not here. Finn, not here. Henry. There we go. Henry there. And Jacob there. Joffrey. There we go. John, Hannah. Joshua, Brent, Keith. Martin. And Ned. Richard. And Sasha. And Will. We're mostly here. This is about to die. And that and oh, right. You're going to switch with Alexander in terms of seating plan. Shoop. Today is Block B. And Will and Alexander. I don't have your lab. I am almost done marking the lab. It needs to be in ASAP. Yep. Nope. We went over it last time. So that was practicing our protons, neutrons, electrons, just sort of in a table, getting used back to the Bohr model of how all of the subatomic particles relate to each other. And then now we're going over electronic structure as a little bit of review of how they're put in the center. So if I was to, what's going on here? Okay. Joffrey, starting off with the first one, what does the Bohr model look like? Yeah. Starting with the first one, how many protons and neutrons does hydrogen have? 0, 1 proton, 0 neutrons. And then what does the electronic structure look like? 1 electron. Going on to helium, and clearly I've put everything right in there. What does the electronic structure look like? 2 electrons. And then the piece de resistance. What does the electronic structure for lithium look like? 2 and then 1. And we've been doing this so long, you probably did most of that automatically. Oh, that looks like a 1. Oh, I'll make that clearly a 2. We fill them up from the inside out. So it starts with 2, 8, 8. So that first one is the one that gets filled. They don't get filled on the outer levels. And then as you fill them, they fill them up until they go out to the next level and the next level and so on. So they fill up from the energy level closest to the nucleus. We are treating them as things, which means it is a Bohr model. So we're not treating them as waves or particle points at this time, which works for most of the things. And the maximum number of electrons in each shell is 2, 8, 8, 18, which you can get from the structure of the atom. And if your reminder from last day, because I believe we did it, on your periodic table. Now that doesn't mean as you fill it up. If we're doing phosphorus, it's 2, 8, 1, 2, 3, 4, 5 in there. However, that doesn't mean its earlier electrons are at these points. We're just using the structure of the periodic table in order to figure out how many electrons are in each shell. So you just count down. So we're going to see later, we skip over these middle ones once they're full, because they do a little something weird. Yeah. Yes, you can. Thank you. In fact, I have a spare next block. And so once I feed Ms. Walensky's cats, I think I'm going to print the data booklet. Sir. How do we draw it? Oh, well, here, little preview. Let's expand on that. Pick an element off of your, or pick an interesting element that would have 18. Iron. Oh, well, that one's easy. So iron, element 26, it's got 26 protons. And now, from here, iron weighs 55.8. So let's say it weighs 56. It's got 26 protons. How many neutrons does it have? Louder? 30. Excellent. After that, it's easy. I count across, well, there's 2 in the first shell. And there's 8 and 8. And then there's 1, 2, 3, 4, 5, 6, 7, 8. So that one probably doesn't look all that unusual. Let's pick an even more interesting one. Let's pick, pardon? Argon. Well, argon doesn't even have any d orbitals. Silver, Ag. Ooh, way down there. Okay, silver's better. So let's do silver, Ag. Silver has 47 protons. Its estimate for the number of neutrons, silver weighs 100, let's say 108. With 47 protons, how many neutrons with that? 52. Hold it. From 108? 61. Neutrons. Now at this point we get 2, and I'm going to stop doing those lines actually. We get 2 electrons, 8, 8, 18, 2, 8, 8, 18, 18, oop. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 in the last one. However, at this point, this is where quantum really helps. If you do sort of a mishmash of the quantum and Bohr model, you actually get this. This first one, 2, that's fine. There are 2 electrons there. But this 8 is not 8. It's a 2, 6. This one's a 2, 6. And this one is a 2, 10, 6. And this one is a 2, 9. Okay? Now, we'll be doing this a little bit later. Let's grouping, where's grouping? Ungroup. One of the reasons that we don't count the middle ones is the order here matters. And it turns out that once this is full, the 10 actually drops down and joins these guys. And so the 10 technically belongs to the 3rd energy level, even though it doesn't get filled until the 4th. Yeah. And so when you have ions for silver, sorry, that's not silver. When you have ions for this one, what was this silver, this last one? Yeah, it was, actually. I lie. Silver here. Those ions might play around with these ones and these ones first. Now that dropping down only really happens once it's full. And it hasn't happened here yet, so it hasn't happened in the valence electron, so it's not going to play around with that probably too much. But if this was, say, tin, then these all would have dropped down, and you'd just be playing with the electrons in those 2 sections. So there's another structure below the what I've taught you. First thing I've shown you is like there's the 2, 8, 8, and you can use that structure. But the way they're blocked also refers to a structure. And it's not those elements in there. It's just that it turns out that the first 2 electrons are in a different energy level than the next 6. And you can see they're also differentiated by block. They're actually fundamentally different. They have a different shape. Have you heard the time-traveling electron theory of the universe? Unlike protons and neutrons, every electron is absolutely identical. There actually can be slight differences in protons. And one of the theories, not theories, one of these guesses by someone, and by someone to Richard Feynman, and I can't remember the other gentleman's name, but both of them very respected physicists, were sort of guessing around. And they're like, what if all the electrons are actually the same electron? So one electron travels forward in time, and then when it gets to the end of the universe, it just travels back in time as a positron. Then it travels forward in time again as an electron, and then it travels back in time as a positron. And just does that over and over and over, and all electrons are actually that electron. And that's why they're all the same. They're all the same because they actually are the same. They don't have to. They move through time. In terms of physics, a positron works out to be what an electron traveling backwards in time. If you do the math and you said an electron's traveling back in time, what would its characteristics be? The only characteristic that would be different is its charge. Now, that doesn't mean positrons are traveling backwards in time, but it could be. Yeah. Oh, positive electron, antimatter. Yeah. One of the reasons this theory hasn't been taken too seriously, even though it was said by some fairly bright people, is that if that's true, where are all the positrons? We should have an equal amount traveling back in time. Unless somehow they all get, annihilated in such a way that they restart their journey, but we never see them. But interesting. Yes? Time has a direction. Oh, we don't know that. Yeah, just like you go forward, you're going forward in time right now, right? How do you do that? No, it would just happen in the same way we go forward. Oh, we don't know. That's why this is a hypothesis. It's never been proven. But one of the things that they say, not they say, but one of the things that sort of makes you go, is you can do some calculations of what the properties of an electron would be if it was moving back in time, mathematically. And the only thing that fundamentally changes is its charge. And a positron is a positive electron that has a positive charge instead of a negative charge, and they exist as antimatter. Antimatter could be matter, regular matter, going backwards in time. All protons in this class are the same. But when you get up there, you'll find that protons of some elements weigh slightly different than protons of other elements, which is weird. Yeah. Yes? Oh, yeah. Okay, we're going to do the next one. Yes? Yes. No. Where? Oh, electron density. That's a probability. So it's not the probability of an individual electron. It's the probability of an area around an atom. And I'm really glad you asked that question because I'm sure that other people have the same. I'll do that right after we do this last one. So for this last one, please draw the energy levels for lithium +1. Yeah, no, that's a really good question. And I'm going to pick on someone like Joshua. Not Joshua, but someone like him. And I'll draw the electron density version over here to answer Sasha's question. Okay, Joshua. Oh, excellent. Well done. Now, if it's an atom and you have 3 protons, how many electrons do you have? No. If I have 3 protons, 3 positives, how many electrons should I have? Yeah. Yes. It's early still. I know. And if you have the same, how many go into the first shell? And the next shell? Yeah, so I'm just reestablishing this. Okay, so that wasn't a trick question. Now, if I have lithium plus 1, I still have 3 protons, but what has happened to the number of electrons? Yeah. So how many electrons do I have? 1 less than 4? The one less than B4. Excellent. Well, how many would that be in a number? It'd be 2. So what would the electronic structure look like? Yeah. That was actually really good because that was very clear to anybody that was confused. We took away that 1 electron, so 1 electron went away, and we have a plus 1 ion. So this is not neutral. This is an ion. Now for Sasha, in terms of what does this look like as an electron density? Because we don't do very much with densities. We tend to draw them still with Bohr and orbitals. But density says they're not, right now we're treating them like they're little things that go circling around the atom, right? And that's, of course, not what electrons are. Throw that away. Go away. Go over here. What it is, if I run a calculation, what I will find is that there is a % chance that I will find the electron, and I can run a simulation that says, what is the chance that I'll find an electron at this point in space? And we tend to represent that with shading. So the darker the color, the more likelihood we'll find that electron. You still find it in other spots. There's very low chances. But essentially, we get almost the same thing. We have an orbital now, but the density of probability in this area is higher than this area. You're more likely to find the electron there. So instead of saying the electron is there, we now go, it's just a high probability of finding there. And that's what we mean by density. And it's still just 1 electron covering all of that. And technically speaking, it's actually 2 electrons covering that. Yeah. Yeah. So that there's a chance it's not there. Yeah. Oh, well, you can calculate the probability. Like the electron's supposed to be here, right next to the atom, but there's a formula you can calculate that they have discovered, a quantum mechanics formula, in which you can say, well, it's supposed to be there, but what's the chance it's actually in tuk-tuk-tuk? And you go, well, tuk-tuk-tuk is this far away, and you run those numbers in, and you go, oh, it's a 0.00000000175% chance. There is a probability you can calculate for any distance. Yes. Yeah, it's just that they're there most of the time. There's a slight probability that they're not. It's a bit like, because that's not just true for electrons, by the way. That's true for every particle, protons and neutrons. Protons have a very high probability, so we say they don't move. But there is a chance that you can calculate that when I take my hand and slam it on the desk, that just by random chance they would move out of my way and my hand would fall right through. There is a chance. It's just really small. I would also like to address this fact that I've seen a TikTok going around that seems to be getting more and more popular, where this comedian says that science doesn't make any sense. And then he says a couple of things that actually don't make sense, so I agree with him. But there's one that he says in which when you ask scientists why your hand doesn't go through the table, science doesn't know why. And we do know why. He also says that space is endless and the endlessness is expanding, and that doesn't make sense. And I would say, yeah, that's actually kind of true. But this part, we know why. And actually, you know why. There's a reason why your hand doesn't go through the table. Does anybody know why? Yeah, but it's mostly empty space. Hey, you're on the right track. Yeah. Because what charge are electrons? Negative. And negative charges? Negative and negative charges repel each other. And that's all that is. And the weak nuclear force that's involved in that is way stronger than things like gravity and other stuff. So they really repel. Real fast. Yeah. Not to go through, but you could do some damage to the atoms. The answer is, yeah, we do that all the time. It's called a particle accelerator. Yeah, and then we smash them into each other, and then we get like radioactive elements as we break nuclei apart. Yeah, so yeah, but I mean, you can't getting your whole hand that fast would be hard. Yeah, and then I think no, over here. Could have been. There's a probability, and you can calculate it. And because there's a probability, you can't say that it's completely impossible. So if someone said, well, I walked through a wall that one time, you're like, it's highly unlikely. But it's highly unlikely in the way scientists say highly unlikely. When other people talk about those kind of probabilities, you would say it's impossible. It's like I saw a advertisement for the movie Don't Look Up, and the guy sits down and is like, there's an asteroid that's going to hit the planet. This is not a spoiler because I haven't seen the movie. It's just the advertisement. And the president or president's aide is like, oh, you can't say 100%. And he's like, look, there's a 99.875%. And he's like, oh, so it's not 100. Let's call it 90% a working number. And they're like, no, I think 70% sounds better. And then they start working. 99 point, that we would call that certain. Scientists will accept any improbability and say, well, it's not 100%. But we know in communicating in public now, don't do that because we learned that from global warming. Yeah. Oh no, they would. Everything would just pass through each other. I haven't done it yet. Yeah. It would feel like nothing. Like the electrons would just pass through. Like you know how in that Rutherford experiment we shot helium atoms through a thin gold foil? It would just be like they would just go through. Yeah, just like whoosh. Yeah. And then I think your hand was up. Yeah. Yes. Parts of it, yeah. Yeah. He's moving his he's using the speed force, which is the word in the DC universe for magic. But anyway, if we were to pretend it's science, he's moving so fast he can adjust where his nuclei are so they never collide with the table and then move it through the table. So that's what I would say he was doing. Oh, good. Yep.
So if you already have your hand in the table, could you really just switch it around, or would it?
Well, keep in mind that probability is like going through. It gets less probable the longer you're doing it.
Yeah.
So, yeah. Oh no, the nuclei would then you would hit something, and then something nuclear would happen. Well, your hand might, and then the rest of the room. Yeah. And maybe the city. Yeah. Yes. Yeah. 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 But you don't have to oh, I shouldn't do that. I mean, right now there's a chance that your butt would do that in your chair, and we're not all standing up all the chance is so low. The chance is low enough we could run the universe as a simulation over and over and over again, a ridiculous amounts of times, and it's not going to happen. Yeah. Even once in the whole universe. So when I say the probability is low, the probability is very low. Okay. Oh, I can't do that calculation. That requires math. That's quite a bit beyond me. What? Maybe. Yeah, I think that would send me down a rabbit hole that I would never recover from. Okay, has everybody done this? How many people have not done it? Yeah, no, I didn't assign for homework. I can't remember how close to the end of class I gave it out. And it might have been right at the very end. Okay. Do it now. You can work with people. In fact, maybe I'll take this moment, a moment, and let's see if I can't start printing off your data tables, which I owe you. Data table, chemistry. No, that's not it. Where's the chemistry 11 data table? Come on. Data booklet. Come on. There we go. That's the chemistry 12 one. There we go. Do I have keys? Where are my keys? There they are. I will be right back. Let's see if I can't get your data booklet. Well, morning, Mel. Not too bad. Do you know what? Do any of our other printers have a stapler in them? Or is it just that one that's broken?
The black and white one does.
Oh, does it?
That should work now. The color one that's working.
Oh, it still has the box and everything there.
Oh, yeah, sorry. They took that side off. Yes, forget it.
Yeah. So the black and white one does. Can they have it in black and white? Probably. two-sided. Hot off the presses. Now, as you do questions from Hebden, use the periodic table either at the back of the book or this one. Do not use ones off the internet. Not because they're necessarily wrong, but if you're checking your answers at the back of the book, they're going to assume you use the one at the back of the book, which is the same as this one. And their decimal places may then be slightly different. Yes. What are you doing? Everybody's working on that sheet. Yeah, but you haven't asked for it either. Yeah, we had it out last day. Yeah. Oh, yours is right there. Oh. Oh, you could. Yes. Yes. Sorry. Masks and everything. I'm like, what is she talking about? Well, come get another one. Come. Yeah, you should know that. Oop, it's not in there. Yeah. But you should know that. There it is. You can see electron densities now. Yeah, Yeah. It's like some students I could name, and certain staff. Little balls of negativity. No.
What's the chart? Or like, how do you find the chart again? The periodic table? What is the order? Is it? No, there's a no. There's like a. It goes plus one, plus two, and then after that. That's the Oh yeah, that's right. It goes up and then down again.
Okay. One second. Pardon?
What's the chart for helium?
You only go up to calcium. 1 to 20. What about them? Because they told you not to. Because they told you not to. Yeah, there you go. What, you're just not going to accept my word for it? How dare you? Yeah. No. I'll explain why in a moment. Someone asked, so this is the first picture of an actual atom. And you can see the electrons. Because really, when they say a picture of the atom, they're only saying pictures of the electrons. And it looks very similar to that electron cloud thing I was talking about. So you have an areas of density. So this would be the first S shell, which will mean more later. This would be the second S shell, depending on the atom. First direction of an excited hydrogen orbital atom. So it's excited, which is why we probably have, if this is a regular one electron atom, if that electron's excited, it might be why it's in an upper orbital in the second orbital here, because of the 2-8 rule. Or maybe, no, that would be the ones there and there. And so you see the area of density for the nucleus, and you see where the electrons are spending a little bit of their time. So, yeah, we actually can see atoms now. And that's like, I can't remember when this was done, but I think it was 2020. When was this printed? 2013. Last update. So, it wasn't 2020, it was 2013. 2020 is probably when I heard about it. Yeah. Pardon? Someone said something. It almost looks. Oh, yeah. Oh, okay. I think that's one of those random facts. Mill Bay firefighters, because what was really important to know this summer? No. I mean, I'm not putting out a fire. And apparently it can't be reached right now, so never mind. No. What's the fire safety level at, and am I allowed to build a campfire? And they would have lots of notices that basically said, no! Yeah. So I just bookmarked them so I could check, because I want to know when was the first time that we could build a campfire. And then when we did, that's why Omni went down and did marshmallows. That was like on the second day that they had dropped the campfire ban after the rain. Okay. Let's do these. Now, I'm not going to draw all these in here, but let's just go around a room and get the electronic structure below. And the electronic structure, I'm just going to draw, if I was doing it for nitrogen with 7 protons, would be 2, 5, for example. And you have an entire diagram inside of there. But the part I'm really interested in is this part down here, the electronic structure. Starting with Will at the back, we'll just go up and down the rows and just tell me what these numbers should be, because they should be really obvious, pedantic, and we can almost chant them like monks. Will, what's this first one? No, that's hydrogen. Helium is way over here. It's kind of covered up by this thing, so we're going to kind of ignore it. That I covered that up. I didn't notice that until just now. How many electrons does it have? 1. So what's this electronic structure? 1, just 1. That's all it is. Moving up, Cahalan, what's helium? stays 4 usually. 2 protons. How many electrons does it have? And how does their structure go? No, not the whole Bohr structure, just the electrons. 2. Sasha? Lithium. Excellent. Oh, they're away. Hyundai. Next one. Okay, keep going. Yep. 2, 3. 2, 4. 2, 5. Nobody in that row. 2, 6. Who's that behind you? There we go. Joffrey. 2, 7. 2, 8. Ooh. Getting good now. Yeah, it's you, Jacob. 2, 8, 1. Yeah, you need the 8 in there. 2, 8, 2. And let's just start at Keith. 2, 8, 3. 2, 8, 4. 2, 8, 5. And we can see the pattern should be coming clear. And then we reached it. Now, the reason I asked you to stop, 2, 8, 8, 1, to, what's the last one? 2, 8, 8, 2. The reason I ask you to stop here is this is where the transition metals start. And I don't want to have to do, because for that, then we'd be at 2, 8, 8, and then here we would have like 12 or something. And right now I want just the simple electronic structure to do some basic things, and so we don't need to do that. So we're going to sort of cross all that out. So now we can sort of answer all of these questions. Predict the electron loss or gain in each column. So here, Jonathan, what are the electrons going to do? Now, first of all, what makes the electronic structure of an atom, so I'm not going to ask you for a prediction, just what makes the electronic structure from last year of an atom stable? What is it like to be? Equal to? Next, well, I can give you a hint, and the hint is, does it like to be, they want to have 4 eggs? Don't listen to Keith. If Keith told you that, that was terrible. He said 4 eggs. Yeah. 4 of them. Just no less, no more. Did you say full? Full rings, no valence electrons. So they need to be full. Can they be empty? Yes. Because if they're empty, then the next one's full, and that works as well. So there's 2 tensions there. One, you can have neutrality where the positives equal the negatives. But that's not actually stable. That's electronically neutral, which is 1 force. But for stability, you need the electronic structure full or empty. So for this one, then I'll go back to Jonathan. Are we gonna get rid of 1? Or are we gonna add, for these ones, add 7, and for that one, add 1? Which one? We add 7? Which is easier, to go get 7 things or get rid of 1? Get rid of 1. So these ones will tend to lose an electron. Now notice hydrogen's here. This is group 1. These are the alkali metals. Hydrogen's not an alkali metal. But The reason we put it there very often is because it does exactly the same thing with its lone electron. It loses one electron. If you lose one electron, what charge are you? Anton. +1. Yes. All of these or just the hydrogen? Yeah, hydrogen can, which is why sometimes you'll see a periodic table and they'll put hydrogen here. Because it can do both. Well, there are periodic tables where they'll actually put it in 2 spots to remind you it can do either. It's not like the alkali metals. It's not in the alkali metal family. We just put it there. Some periodic tables actually just detach it, put it a little above to show like it's that if you have a friend circle, like you think of all the alkali metals as friends with similar properties, and they all like to do the same things. Hydrogen's like that annoying one that just shows up anyway. It clearly doesn't belong, but likes to do the same sort of things, and you're always trying to get rid of him, but he always shows up. Everybody's too polite to make them go away. Hydrogen's that. It's a family of 1. Yeah. Okay. Next one. Oops. Cahalan. For the next one, are we going to lose those 2 electrons, or are we going to gain 6? So we're going to lose 2 electrons. What charge would it become? +2. And then, of course, we have this one. And that, Donald, what are we going to do with the electrons in there? Lose 3. What charge would it become? +3. Jacob. I'm doing well. How are you doing? Excellent. What's going to happen in here? What? No, you can't pass. That's actually a teacher's college rule. If you let a school pass, not a school. Yeah, we don't pass anybody in the course. They all fail. No. If you let a student pass and not answer a question, then what does immediately everybody do? Yeah, nobody answers questions. That would be unfair. But I will give you a hint. Well, the hint is you just have to say whether it would gain 4 or lose 4. Either. Either gain 4 or lose 4, which means that its charge is plus or minus 4. We can go either way. Carbon has either ability, as does silicon. Part of what plays into the properties of an organic molecule and all of organic chemistry. Anton. For nitrogen, gain 3, lose 5. Sorry? Yeah, this is the -3. So what is it doing with its electrons? Yeah. So I'm going to write a different color because it's so close. Gain 3, if that makes, if you can read that. And Richard. Gain 2. What's his charge? And the next column, Jonathan. -1. What does it do? Adds 1. And the piece de resistance. The Hyundai. Nothing. Yeah. What's its charge then? 0. So not only are they completely stable, they also have neutrality of charge. So there's no force to make them do something. They don't have that tension. They called them noble gases. But you know, if it was in today's language, we would call them, you know, the 1% of the 1%. They just have so much, they don't do anything. Other people do things for them. Yes? Yep. Yeah. Someone had asked that. So that way, it can also be put here. It fills its shell, so it can do that. If it's here and you take an electron away, it's acid. If you add one, we call that the hydride ion, and it's -1. It's more rare. You don't encounter it very often, so it is something that doesn't happen as often, but it does happen. Sasha? What is the charge for? I heard, what is the charge for the one where we quit eyes? Oh, yeah, so it could be either. Well, another way to say it, carbon has twice the chance of a date on a Saturday night. It depends on the date. So if carbon is with someone that wants to give carbon electrons, then carbon accepts electrons. So, we look at the date. So if carbon is with nitrogen, well, nitrogen wants to get 3 electrons. So carbon's the equivalent of +4, that's -3. So we would have C3N4, and we could call that carbon nitride. That is a thing that carbon can do. But if carbon is with, say, aluminum carbide, then aluminum, whereas there, wants to get rid of 3, and carbon now will accept them. So we can say carbon's -4, that's +3. And Al4C3. And so what it's doing depends on who that carbon is placed with. Yeah. Someone else's hand was up. No? So yeah, for carbon we just have to look at their partner, and then we can figure out what carbon's going to do. Other questions? And a couple of definitions down here that you have it printed, but highlight if you need to rewrite this in your notes. Columns are known as families or groups, and rows are known as periods. So this is one family, and we're going to do the families of the periodic table in a little bit, like the alkaline earth, transition metals, all that sort of thing. But just so you know, when I refer to a family, I'm referring to a vertical column. If I'm referring to an area across, I'm referring to it as one period, like a period of time. The reason we call them a period is because properties reappear periodically. +1, +2, +3, plus or -4, -3, -2, -1, 0, and then +1 again. So we have a new period of the exact same properties. It repeats. And that's why it's called the periodic table. The properties of the elements reoccur periodically. The old periodic table did not use atomic number. It tried to use mass. Although they would correct it based on properties, but they couldn't explain certain things. When you're doing things like mass, iodine at 126.9 weighs less than tellurium at 127.6. And so if you did it by mass, before you knew about atomic number, you'd think that those should be flipped. This one's heavier. It should be ahead. However, based on properties, tellurium has a lot more in common with selenium and polonium, and iodine is a -1, very reactive non-metal, and it shares a lot in problem with bromine, chlorine, and fluorine. So they would correctly put them together. Mendeleev, who made the periodic table, he did that. He had little cards where he would describe the elements and all their properties, and he would place them in families. And by mass, that would give you the rough ordering, but they knew enough to not put them in that order. And now we just know it's the number of protons. That's what determines the properties, because the number of protons determines the number of electrons, which then determines what kind of charges you're going to get. Okay? Okay. The atomic mass unit. Write this down. Now, for this, we still use this definition, and you'll still use it in university. They've redefined it because an AMU is the mass of one proton and or the mass of one neutron. And it turns out that what just happened there? There we go. The mass of one proton and the mass of one neutron are the same. It turns out a neutron weighs a very tiny bit more. It weighs about enough mass to be enough mass to be an electron that's added to the proton to become a neutron. And it makes kind of sense, because if you look at the radioactive decay of some elements, neutrons will spit out an electron, beta radiation, and become a proton. And so protons in different atoms can also weigh very slightly different amounts too. Not enough that it's going to affect our calculations in here, but if you're calculating for something very precise at a university level and you're investigating the heart of the universe, well, then it starts to matter. For our definition, and the definition you will use most of the time, they used carbon. And the reason they use carbon is because carbon is near and dear to us, as carbon is carbon chemistry. So this is organic chemistry. And we are humans, and so we use a lot of organic chemistry, and so we define it based on carbon. If you were in a different alien species and they were based on ammonia, maybe they would use nitrogen for theirs. So that's how we do it. So one AMU is 1/12 the mass. And carbon has 6 protons, 6 neutrons, so it divides it evenly between them. So one AMU is the average mass of a proton and neutron. Atomic mass, is, as we've said, is the average of all mass numbers of all the naturally occurring isotopes of that element. And the first example I'm going to give you is for carbon-12 and carbon-14. Carbon-14 is actually being made right now in the upper atmosphere. So ionizing radiation will hit some nitrogen. It will actually turn it into carbon, and instead of being nitrogen with 14, it'll be carbon with 14. This is highly radioactive. There's not very much of it, but there is a little. And because it's made in the atmosphere, that means all the living things breathe it in. And then once you die and your metabolism stops, you don't breathe any more in, and it never changes, and so it slowly starts to decay. This is how we're able to radioactively date things that were once living. It's because the amount of radiation that you have in you from just existing is constant due to this carbon-14 being created in the atmosphere. And once you die, you don't get any more, so you can just say, oh, once they died, it wasn't being replaced, and there's this much left, therefore, how old is the sample? It only works for a certain amount of time, but yeah. Oh, yeah, it's gotten better because our sampling techniques. It used to be only like, I think it used to only be like 60,000 years at the most, but I think they've bumped it up a bit since then because they're more precise. And the amount, by the way, in the atmosphere does change over time. And to get really precise results, you want to know how much it changes. So what they use is tree rings. So tree rings will have a pattern based on growth. And some years will be big because of lots of rain, and some years will be low because of low rain. And maybe you get a few low years in a row, and then you have a lot of rain, and you get a big year. Well, that makes a particular pattern like a barcode, and that'll be same for all the trees in the area because they had the same years. And all the trees will die at different times, and so you can overlap them. So they have a tree ring history of various dates going back thousands of years from old trees that they sampled, and they can sample in each ring as well. And so they can get the amount that was in the atmosphere at each time. Yeah. Ice? If there's carbon trapped in it, yes. So if it has air bubbles, pardon? Well, if you have an air bubble, I mean, water's H2O, so there's no carbon in the water. But if there's some organic material, or there's some air bubbles, and I don't know the size of an air sample you'd need, but you should be able to. Yeah. Yeah, I would guess so. Yep. Right. Yes. So what are we doing here? Now, this first calculation is pretty easy. I want you to do it, however, this way. And in terms of this calculation, if I have this is just a reminder of what percent is. So 50% just means 50 over 100. Oh, sorry. 50% is 0.5 times 100, or you can take the fraction 50 over 100 times 100, or 5 over 10 times 100. So all percent means is times 100, right? I've encountered a few students over the years who somehow managed not to do percent. So 50% of all carbon was carbon-14, and 50% of all carbon was carbon-12. Then we would calculate the atomic mass this way. And I want you to write this down as an example, even though you could do it very easily. What is the average if it's 14 and 12? 50% of each. 13. You can do that in your head. But I don't want you to do it that way because we're going to do it in ways that are much more difficult than that. So I want you to know the answer in advance to see that it works. Sure. Okay. 9:23. We got a few minutes. So start off this way. We've got 14 carbon. So 14 AMUs times our fraction, 50 over 100, or you can just 0.5 if you do that in your head. And what is 14 times 0.5? 7. And then we have our 12 carbon at 12 AMUs. I am writing down all the units. In chemistry, you have to write down all of your units. Just to be aware for when I'm marking your work, Hebden or otherwise, I'll expect to see all of your units. Times 50 over 100, so that's its percentage. What is 12 times 0.5? 6. The atomic mass, the average. Remember, these are mass numbers. That's the average. So we're now dealing with the atomic mass. You just add up the percentages. Right? Does anybody have any questions about what I did there? The procedure, how I calculated it? Yes. Can I explain for one more time for those in the back? For all of those. So I took the mass number, multiply it by the percentage that there was of it. So that 50 over 100 comes from here because 50% just means 50 over 100. Or 0.5 if you want to do it right away. And 14 times 0.5 is 7. You're allowed to use your calculators for this too. So 0.5 is just the same as saying half. 12 times 0.5 is 6. And so I have the masses that are present from the percent that you have. So by adding them up, I get what is the average mass of 100% of carbon, when 50% is carbon-14 and 50% is carbon-12. Yes? No. This is the average. I add them. This is from 50%, and this is from 50%. So I have to add them together to get 100%. So this process has done that. If I just did a straight average, I could go 14 plus 12 divided by 2. But that won't work. That only works if I have even numbers. Your method of calculating averages for math class only works if you have the same percent of each one. This is a way of calculating if you only have like 10% of each one. Yes? So the atomic mass is an average. Oh, because it's an average of these. So what is the average if half of it's 14 and the other half is 12? It's 13. So we know it's 13 in advance. And then I do this calculation to see, we got the same number. So we did get the right number. So we know this is right both in our head from looking at it. To calculate the average another way, you don't just take 14 plus 12 divided by 2. You can calculate it from the percentage. You can say, well, the weight of half of it, if half of it's carbon 14, then 50% of 14 is 7. So we're getting 7 from one half and 6 from the other. So in total, we've got 13 for a total weight. Does that make sense? Okay. I would like you to do that again then, but with more accurate numbers. So do exactly the same thing, but we're not using 50 and 50 because the real numbers aren't 50 and 50. They're closer to 5 and 95. So carbon 14 is not present in very high amounts. Carbon 12 is present in much larger amounts. It's the regular carbon. What mass do you get when you do it this way? And I'm going to come around and I would like to see your answer. Sure. Yeah. So I want you to use this exact same process. So you've got carbon 14, but you have a different percentage. So you don't have 50%, you have 5%. And show me the number you do get. First, write out all the calculations. Oh, you're calculating the first one? Yep. Can you write on that? Like write on your... No, with like a pen or anything? When? Okay. Excellent. Are you confident? Excellent. Then you don't need me. You're just confident. Remember, if you're confident enough, you can become president. You don't need to be right. Right is second. Yeah. Yeah. Something, is that a... Yes, I think so. Well, what is 14 times 5 divided by 100? Why are you putting everything in fractions? No, stop that. You have to use decimals for everything now. We're going to be doing significant figures later. You have to have, because fractions can't show error. Fractions are evil. That's for math class. We don't care about math class. They're dumb. You need decimals for everything, because we're going to be showing error. The rest of that number doesn't matter. It's 0.70 forever, according to mathematicians, but they're wrong. This is the class we get to show you why 2 plus 2 does equal 5 sometimes. So you have to use decimals. Good. You're on the right track. Yeah. 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 Now we're looking at cooking with gas. As I'm coming around to take a look then, please start the next one. Yeah, I know. The next one, example 3, what? Has those 14, 13, and 12 with 0.5, 0.03, and 99.47. Much more closer to the real, actual numbers. And there's more than one isotope. Whoa! Your homework tonight is that I'm updating the Hebden with some of these problems. So I'll move those bars down. So tonight, just continue on with your Hebden. And if the bell happens to go in the next minute, which it may, finish off this problem. The answer for the last one, you should get 12.1. I think I've come to almost everybody. There's just a couple more I need to check, and I want to see those. And you'll know that you're on the right track with this one if you get 12, at least something along the lines of 12.01. But include all the decimals that you know of. Where's your last one? There you go. Calculations for the last one. Good, and you got all units, calculations for the last one. So for you, you have to have units. And you have to show all of your work. Yeah. You know that whole developing, emerging, proficient stuff they're going to be doing? Proficient is going to be in the communication section that you show all your units. So, no. That's just analysis. That's just one of the 3 things you need to be able to do. And to be honest, if even before this, I would have said exactly the same thing because the units matter. We once took a Mars probe that the U.S. and European Union co-built, and we slammed it into the surface of Mars at 1,000 pieces because one scientific team was using pound force, and the other one was using kilogram force, and they forgot to communicate what units they were using, and instead of slowing down and deaccelerating to Mars and gently landing, it sped up and killed it. Units are really important when communicating scientifically. And it's going to become more important later when we do other things. So I'd want you in the practice now. I don't think so, actually. Did you? I don't see a calculation here. Yeah, that one's over 100, but why isn't that over 100 and why isn't that over 100? Yeah. And then they're not percentages. Show the entire calculation. Yes. Show me your previous one. I didn't see your previous one. Oh, you need the previous one first because I can't show you this one until you've done the other one. Yeah, so do that one. And the answer to that one is do that tonight for prep. And the answer to that, you're in Rogers, right? So, Mr. Snow, yeah, and I'm around in Privet this afternoon. The answer to that one should be 12.1. If you got that, then go on to the next one. Okay? You have done something very wrong. All of those have to be divided by 100, yes. So the answer to the last one should be around 12. It should be 12.0103. If you don't get exactly that number, you've done it wrong. Even if you get 12.0104, you have done some sort of rounding that makes it incorrect. Lots of stuff. So you, of course, consulted the live stream, got notes off of a study buddy, and are up to date?
I got notes from the study buddy.
Oh, excellent.
Yeah.
So what did we miss? Did you just photocopy the notes?
I just asked what we got.
Oh, you didn't write them down? So, every time you miss a class, you have to go and actually get the notes, go through them so you do know what's going on, then come see me the questions. We got tutorial tomorrow, right? Sir.